Hi, my name's Andy Robb. Welcome to my feasibility assessment of Google Loon. I guess this is more just a feasibility assessment of some of the ideas that are behind Google Loon. I'm going to walk this through. If the slide doesn't advance on its own, just hit forward and it should go. Hopefully you have your speakers on or you're not even hearing me right now. So the purpose of this presentation, originally I had put this together. I just wanted to put a few slides in to show my experience with some balloon programs and space programs at Boeing. But then I thought, that's not so important. You guys probably won't care. So instead, I just decided to take a crack at some of the goals, the stated goals of like Google Loon for Internet in the Sky, and see if I felt it was feasible and how I'd make that work out. And so I just threw some slides together. Hopefully you'll take a look through, and maybe I did something interesting. Maybe I demonstrated I'm not an idiot. So hopefully I have more good than bad in there. And if you ever think of hiring, pick me up or hit me up or get a hold of me. I stuck my resume in the end. And the reason I say that is because after working through this, I'm sold that there's a lot of potential in this program, and I like working on things that I believe in. So I don't want to call this Google Loon because I don't know where Google is actually going to take their Loon program in the future. But I've seen some of the videos online. I just decided to dress it on my own and figure out based on the goals what I felt was reasonable. And what I think is reasonable is a small balloon with a sub 10 kilogram payload. So my payload was like 8.5 kilograms when I worked out what I felt was reasonable weights. Operational lifetime of 5 years. Yep, 5 years. I think 5 years is doable, and a coverage of about ground coverage spot of 500 kilometers squared. And the key concepts on what I felt would be a smart, well-optimized design would be extreme power efficiency of the electronics and of the RF and power amplifiers, because that sets the weight of the batteries, which is one of the dominant issues. And then an active buoyancy control system, where instead of having a super pressure balloon or a zero pressure balloon, you have a balloon that is essentially a zero pressure balloon, but it's a closed system where during the daytime as it warms up, you pump hydrogen or you pump your buoyant gas into a pressure vessel, and then at night you vent gas from the pressure vessel back into the balloon. And if you could do that extremely lightweight, which I believe you can, and I'll talk about why, you can get exceptional lifetimes on the balloon because you're not fatiguing the skins and you're not having any high internal pressure, which in the case of even a tiny pore would cause leakage over the course of years. Okay, so at Boeing, I've worked a handful of programs. One of the things I've been doing a lot of work on is like very low power sensors and also on current mapping sensors for lightning. So we can actually take these little Rogowski coils, we can put them on structure, and we can map how electrical currents flow across complex structure. And one of the things we wanted to do with these was basically marry these to a small little computer and data logger and a GPS tracker so that we could put them up with aluminum wires with weather balloons into storms and measure actual lightning strikes cloud to cloud in storms. And the reason we want to do that is just to look at what the threat is that our aircraft have to fly through. The data that we have, we got a pretty small subset of data, mostly given to us by NASA Langley as part of their Storm Hazards Research Program. That's what today's lightning certification specs are based off of for in-flight strikes and cloud-to-cloud strikes. And there's just a hole in the data in that we have a data on a very narrow subset. We don't have data from all over the world, and storms behave differently across the planet. It'd be good to get that data. So we propose this of just building a bunch of these, giving them to different universities and weather research groups so that they could go out and measure data and then hopefully share it with us. But that program never made it off the ground, simply due to concerns about liability. What if a wire blows into a power line, or what if lightning hits one of the grad students and they get killed? And then also there's a business case behind it of what if we discover that the threats in some areas are much worse? Boeing doesn't want to have to go and redesign things. It's better to not look for data that has a bad impact to the company. So, and I get that. So we dropped it and never moved forward. But I learned a decent bit about the utility of the balloons for low cost stuff. And so when I heard about Google Loon, I definitely wanted to look into that in depth, and I spent a lot more time than what you're going to see in these slides, but trying to be brief. So uh, a, a reasonable working concept, and we're back to off of the Boeing stuff, back to the me assessing Google Loon or Andy's Loon, I guess. Um, so 24-foot wide balloon, hydrogen I think is a good choice of gases to use because it's so cheap and available. But uh, instead of a pressure balloon, a closed system with active buoyancy control. So during the day, that balloon warms up and you pump hydrogen out of the balloon into the pressure tank, right? So that way, as you warm up, you're bringing the buoyancy of the balloon down by pumping hydrogen out. And at nighttime, when it's cooling off and you need extra buoyancy, you just vent from the tank into the balloon. The nice thing about that is that you're pumping during the day, and during the day you have extra power, so you're not running off batteries to do this. Uh, Another useful concept would be a methanol reformer. Methanol is a great way to generate hydrogen when you need it. So methanol water mixtures don't freeze at low temperature, so you can keep them in a liquid form on board the payload. And then you really maximize the electrical efficiency so you can minimize the battery weight. So the driving requirements for what I put together is essentially the covered spot area of 500 kilometers squared. I just used 500 kilometers squared because it seemed like a good round number. I think you guys are shooting for something much larger. I just decided to go smaller and cheaper. And then 50-kilometer backhaul, so that's node to node distances, and then minimizing the cost. Uh, when I look at the cost, I don't know what's reasonable. I mean, I know what DirecTV pays for their spot coverage, which you can look up roughly what it costs to build a comm satellite and to launch it, and how many they have. So they got 5 billion or so in assets in the sky just to cover North America. And so if you can launch 50,000 nodes and get the same aerial coverage, uh, for $2,000 a piece, then you're looking at $100 million to do kind of the same thing, which is way cheaper. And so that is definitely a disruptive, revolutionary technology if this works. And so I think there's a strong business case behind it. So I did a quick link budget, 500 kilometers squared. That's 12.8 kilometer radius, and it's easy to figure out, based on just a channel bandwidth on the ground, 10 to 20 megahertz, what the noise is going to be, the thermal noise, right? And then you got 12 dB on top of that from your amplifier and your antenna on the ground. It gives you minus 89 dBm for the system, and that's extra margin on top of that puts you at like minus 77 dBm as your communication threshold. So to get that on the ground, what do you need in the air? What do you need pumping out in the air? Well, I just assumed that you had 6 dBi antenna in the air and a 9 dBi on the ground. That means the guy on the ground has to have the higher antenna, which I think is smart. Let them book the higher weight on the ground, or do multiple antennas on the ground to get that gain in like a diversity configuration. And it puts you at 2 watts out in the air, and at 33% system efficiency, that's 6 watts. Add on another 1 for margin, and then you got a 7-watt system. So that's 7 watts is the access link. On the backhaul, you've got 4 antennas, but you can do higher gains on the backhaul because you have you can direct them through out on like sector antennas, just cover 90-degree sectors, and have very narrow elevation bands, because if all the nodes are going to be kind of at the same elevation, then you can direct your energy through a narrow elevation band and get higher gains. And so maybe 10 watts for the backhaul. So that gives you a total of, with you add in 2 watts for computing and routing, of 19 watts nighttime operation. And nighttime, of course, varies depending on where you are in the world. So if you need to be at high latitudes, then you've got to carry like 400 watt hours of batteries. So I think if I looked into the batteries as well, I think probably the best pick are automotive grade batteries because they have good cycle lives. A123 systems, I mean, at least the automotive manufacturers are qualifying it for cycle life, right? And they're doing a good job. Where you can get commercial off-the-shelf batteries that have better power densities, but they're just not going to give you the same cycle life. So daytime power consumption, you still got 19 watts from the nighttime power consumption, plus in my system, you have a ballast pump. You have a pump that takes the hydrogen out of the balloon and into a tank. and a methanol reformer, which isn't going to take that much energy. But I just booked 60 watts for that system, and battery charge and heaters 75 watts during the day, so 154 watts consumed. So at 77% conversion efficiency, you need like 200 watts of solar cell, and I think thin films are the good choice for that. Thin films you can deposit on glass, and you can get very thin glass. So tempered glass in the 0.2 millimeter range, that's easily commercially available. So you can just deposit thin film on glass, seal it in, and then mount that to like a balsa wood isogrid. And isogrid structures are very efficient, and balsa wood is an extraordinary structure material when you look at high stiffness and low weight. And I'm totally serious about that. Some people think I'm crazy when I say that, but balsa wood and Sitka spruce are two excellent choices. We use those today still in aircraft, but primarily only in like sealed in cores, like composite face sheets and then cores that are made of balsa wood, because uh, you know, at low elevations you can absorb moisture, you can get wet, you can get rained on, and you can get decay issues, but you will never have that at altitude. So it's a perfect choice for high altitude stuff. Uh, Solar array optimizations, I would go for a gimbaled solar array, because if you have to operate at very high latitudes again, and again, particularly in the wintertime where the sun is going to be low on the horizon, you want to be able to point those solar arrays at the sun. And two-axis gimbals, you could do those cheap and light. So when I look at the total weight of the system, the battery pack dominates. You know, you got batteries and insulation for the batteries, and on my system that's 3.4 kilograms, a solar array of 1.5 kilograms, and those are driven again by electrical efficiencies. So fighting down the electrical efficiencies brings down your major weight your major weight drivers. Uh, and then the weight of the systems, you know, they feed the volume of the size of the balloon, and the volume of the balloon sets the amount of pressure vessel you need. And so gas ballasting is another big one that kind of falls behind the electrical efficiency. So, uh, so yeah, I think hydrogen's good. Uh, if I was going to do a balloon, I would put a lot of effort into for long lifetime, something that's very UV stable, ozone stable. So PVDF or PVF would be good choices. And the other thing is that if you do laminates, if you laminate the PVDF or PVF with aluminum, then you can then surface treat the aluminum to give it what you would consider optimum optical properties. So the solar absorptivity of aluminum is already really low. Uh, you'll probably want to bring the emissivity up a little bit so that it radiates heat away a little better during the day, but not so much that it freezes, it radiates a whole lot away at night. So finding that sweet spot of emissivity and solar absorptivity is an interesting area of research, because by doing that you can find out what is the optimum treatment for the skin that minimizes the temperature differential day to night, because minimizing the temperature differential day to night minimizes the amount of volume of gas you have to store to maintain buoyancy. Uh, so in my system, that buoyancy is maintained through an external tank, and you could use the same system to control the altitude by bringing it up and down in altitude. Uh, I don't know how often that operation would happen at night, so I didn't book any battery allocation for that. So that might be a hole in this design. But the tank itself, you would do that. You would optimally do that with composites, right? I mean, if you did it in Kevlar or Spectra, you could have a very lightweight tank. Composite tanks are tough to do because you cut through them and you induce stress risers around the holes. Metals are a little easier. It's just very thin walls are tough to manufacture in metals unless you do some interesting techniques. Superplastic forming is one of those techniques that you might look into, because you can superplastic form titanium and you can superplastic form aluminum lithium, both of which are very good lightweight materials to use for this. The pump, I have no idea what pump you would use, what would be the optimum pump. But I would think for going from 1 to 44 psi, which is about what my numbers turn out to be for this system, two-stage might be all right, where you do like a diaphragm pump and then a linear piston pump. If you could get it from 30 to 50% efficiency, that is great. And the reason is you don't want to suck up too much electrical draw. the worksheet I put together for the storage tank, if you had a 0.35 meter radius tank and a temperature variation of 10 degrees Kelvin for my balloon, then you end up with 44 psi in that tank. And to pump that over 6 hours during the day uh, is 22 watts at 50% efficiency. So if you're 25% efficiency, then you're at 44 watts draw, which is doable. And the total weight for this system out of a 2090 aluminum lithium is 1.4 kilograms. In my weight spreadsheet, I booked that up to 1.8 to give myself a little extra margin. So there's already margin in the design. If anybody is interested and they actually want the data or the spreadsheets, I can send it to them. So I think PVDF is a good choice of materials for the film on that balloon, and the reason is it has some excellent properties for the environments that it's going to face. It's very UV and ozone stable. It's tough. It's reliable, and 3M makes that the Dyneon PVDF films with some plasticizer they add in for extended low temperature performance. And basically, it gives them plasticity below the glass transition temperature, and so they're reporting a brittleness temperature of less than minus 55 degrees Celsius, which makes it an excellent candidate for the temperature ranges that this system would operate in. So, and then lastly, the PVDF has a very low permeability to hydrogen and helium gas. And I've calculated the loss rates out. We'll talk about that later. Uh, on the balloon spreadsheet, where I figured out the optimal size balloon, given the size I have at 7.47% sea level buoyancy because of the density change up there, 3.7 meter radius balloon seems reasonable. That gives me a little over 8.5 kilograms of payload, so it's well matched to what I need. For the basically the aerial density or the aerial weights of the balloon film, I put in 5% for the seams. You don't have to use load tapes on something like this because it's not a super pressure balloon, so you can get away with I think lighter seams. Now the lifetime, as I said, the PVDF is pretty good for permeability against hydrogen and helium, and there's some backup slides that talk about this as well if you're curious. But the PVDF loses about a little over a liter a day, so essentially when you take into account that that liter is at 7.4% of sea level density, then that's 1.4 moles per year. Well, if you got 600 grams of methanol water mix on board, that's 12 moles of reactants. It gives you 36 moles of hydrogen. And so in that case, you have over 25 years of hydrogen time essentially. So I mean that gives you some nice margin over leaks. And in that case, as long as you can maintain a leak-free balloon, that means that your reliability is going to be set by the batteries. So the batteries, a cycle time of 3,000 days gives you like 8.2 years. I mean, assuming that you can maintain good reliability on all the rest of the components, but I think that's definitely doable. So one of the big features of the design that I talked about before was electrical efficiency, because electrical efficiency, particularly for nighttime operations, that sets the weight of the batteries, that sets the size of the solar panels, and then the weight of those two systems, battery and solar power, that largely drives the size of the balloon, and the size and the volume of the balloon drives the requirements for compressed hydrogen storage, which then spirals back into the design. So if efficiency goes down, your weight will spiral upwards, and efficiency goes up, your weight spirals down. So a great strategy is to really focus your efforts on power consumption and power efficiencies at pretty much all costs. I mean, it would be okay to sacrifice a lot to get power consumption down, because it just brings the weight out of the system. So to do that, electrical optimizations that would be worth looking into would be very well optimized gallium nitride power amplifiers, because those amplifiers are going to be a major driver of your efficiency. TriPoint makes some that I found some spec sheets for that looked all right, but that's 35, 36% efficiency at these temperature ranges. If you can find a way or work with a vendor to get up closer to 50% efficiency or better, that would be awesome. Power supplies are always an easy, low-hanging fruit, right? Just get rid of the commercial off-the-shelf power supplies and find a custom power solution, even if it's a bit heavy, that gives you 90% plus power conversion efficiencies. And then antennas, get the high gains on the ground. Just go for something efficient on the aircraft or on the balloon. Um, and then software power save modes is always useful things to try to implement to make the network more efficient. And then ASICs provide better power than FPGAs. FPGAs provide better power than like like an Intel Atom processor or something. Uh, and so power is the biggest issue. Weight is secondary on the electrical stuff, but you want to reduce the PCB mass, the weights of the printed circuit boards. So you can steal a lot of techniques from the space guys here, and use thin S glass rather than E glass, and you don't have to use glass epoxy. There's other resins that are lighter. You can just do two-sided boards. If you can avoid using multi-layer boards, then just go two-sided and make them as thin as possible. And then again, do away with commercial off the shelf, because if you do commercial off the shelf, then you inherit the electrical designs and the poor weight and power efficiencies of whatever that vendor is. So antennas are important because the antenna is what spreads that RF energy out on your spot below. And you want to choose an antenna that gives you a relatively uniform distribution of energy over the spot area, but without a lot of energy wasted outside of the spot. And so you want kind of a flat antenna pattern over the beam width of that antenna. I think a good choice for this, if I had to choose right now, knowing nothing else, I would pick a circularly polarized antenna, because you don't have good fixed orientation up there, right? So I would go for a 7.8 dBi tapered BHA, the bifilar helical antennas. And I saw some designs online that seemed promising, and this was just one of them. So radiation effects are something I want to talk about. Radiation effects, that's an important reliability driver and something people will overlook. But at 65,000 feet, you're going to get large neutron fluxes. And actually, at that altitude, it's worse than the aircraft experience, because at 65,000 feet, you have even less shielding than, say, commercial air traffic at 40,000. So you'll have primary cosmic rays as well, and you can upset your systems. You can flip bits. You can take a memory and flip it from a 0 to a 1 or a 1 to a 0, and you can latch up parts, which is where you freeze up CMOS devices, and you can even burn parts out entirely. Particularly higher voltage stuff is susceptible. I put some slides down here. If you look on the lower right-hand side, there's a memory upset rate for versus altitude and neutron flux at altitude. So that upset rate is just SRAM in terms of upsets per day per 10 to the 7 bits, or 1 e to the 7 bits. So to deal with radiation effects, you just want to avoid commercial off the shelf, because you never know what kind of poor designs you're going to get with commercial off the shelf, or what parts you're going to get. Use error correcting memory, error correcting code, single layer flash, not multi-layer flash. And CMOS devices, particularly anything that's 5 volts or over, you want to limit supply currents and use Watchdog. So Watchdog just interrupts the power if it detects a latch up. So you do that, and you'd be able to deal with occasional resets in the network, and I think you'll be in fine shape. So just wrapping things up here, thank you for making it so far. But the total cost of the system that I put together here, in my just rough estimate, is about 2.6K. It's a small balloon, smaller than yours, of the 8.5 kilogram payload, but I think it's feasible to do something like this, a small, lightweight, efficient system with a very, very, very long lifetime, like 5-year plus lifetime, which will really be dependent upon the reliability of the electronics and the reliability of the batteries, and I suppose the pump as well on that pressure vessel. But a system like this could provide access link ground coverage of 500 kilometers squared, and if you wanted to, say, double that area coverage, I don't think it would take that much more effort to kind of tweak the design to go to a slightly bigger balloon, a little bit more batteries, or if you didn't want to put bigger batteries on, then you could fight the efficiency side and attempt to get much higher electrical efficiencies That way that the amount of power you do have, you can distribute more effectively over large areas. And then here's backup section where I just got some ideas as to things you could chase. At this point, you're welcome to flip through. The narrations are not going to make sense because some of these were slides that were actually in my presentation before, and I said, ah, to heck with it, I'm just going to throw them in backup. So the slide timings and what I say may not fit right if you listen to it, but you can probably pull some interesting information out of it. So one of the things I want to talk about is just the cool technology that you might want to chase for a system like this, which would be a methanol reformer. And a methanol reformer that just takes methanol and water and it catalytically reacts it to produce hydrogen gas. And so it's a very lightweight, compact way of storing hydrogen. And the nice thing about methanol water mixtures is that they don't freeze at the temperatures you're looking at. It will stay liquid. The other nice thing is that it's an exothermic reaction. So once you get it going, once you heat the catalyst up to enough that it starts to decompose the methanol water mixture into, I guess at that point it's methanol steam, but the methanol steam gas into hydrogen gas, then all you have to do is just not cool it off or keep the flow going, and it'll just continue to generate hydrogen gas without any extra energy being pumped in. So the hydrogen storage tank, I mean, obviously that's a focus area for optimization. Optical property optimization of the balloon, to keep the day-night temperature variation as low as possible. Structural insulation. So, multi-layer insulation is widely used as multi-layer insulation films, but if it's not unreasonable to say, hey, we could try to get some structural benefit out of that. So that's making insulation panels that are very lightweight, have excellent insulation properties, and are structural. I think it's a useful focus area. Ultra low weight PCBs, you can steal a ton of technology from just the Boeing and Lockheed and TRW for electronics manufacturing of satellites. Antenna optimizations, obviously. And then solar cell gimbals, that's also kind of an obvious one. Power saving electronics, clearly that is something to focus on a design like this where the power efficiency is the dominant issue. And then preamps for the antennas, that's fine. You can for the preamps you can take advantage of the low temperatures up there to get more basically less thermal noise in the front ends of your receivers. And then PVC, PVF, they're cheaper materials than PVDF, and with the right plasticizer you can probably get the brittleness temperature down enough that they're usable. And then the ground antenna system, if you could do diversity antennas or steered high gain antenna, I think that puts more complexity on the ground and less in the air, which is overall goodness. And the first is that at the altitudes you're working with, 65,000 feet, if you look at the absorption bands for water vapor and oxygen, at high altitudes, at cold temperature, that vapor pressure of water is extremely low, and you're above most of the atmosphere anyway. So if you used bandwidth for node-to-node communication that fell, say, at 23 gigahertz or at 180 gigahertz, there is probably not much else in the world that uses those frequency ranges, just because at the ground they're very inefficient. But at that altitude, that would be an excellent area to pick off some frequency. The next thing I would say would be try to build supernodes. If you could go higher, 70,000, 80,000 feet, optimize your system for high altitudes, build a bigger balloon, and try to do very long line of sight communications. So 500 kilometers node to node. You could just put those up across the oceans and essentially get high data transfer rates across this network of nodes of just 50 of them would go from Japan to London, and it's a heck of a lot cheaper than a transoceanic cable. And if you can make them very low latency, and you could get them to go over polar routes and operate, particularly during the summertime, then you could have very low latency communications from Asia to North America to Europe, and have latency that's much lower than the fiber optic lines that are running underneath the ocean. And in that case, you could probably sell bandwidth to high frequency traders for quite a bit of money. Whether it's enough to offset your design costs of the system, I don't know. It's just an idea. And the other thing I thought about in terms of vulnerabilities is simply that uh, if you want to fly these around the world and you have to fly them through everybody's territory, uh, they could be pretty easy for somebody to bring down if they wanted to, military. And I imagine that most places in the world would not be threatened by Google flying free internet into their area or cheap internet into their area. In fact, they would welcome them. But there are a few places where you just have crazy people, like North Korea, where I'm sure they would put some serious effort into shooting them down. And if you really wanted to overfly their territory, then there's not much you can do to survive a laser weapon or even ground-based high-power microwave. But I'd say the best defense is just don't be noticed, keep a low radar cross-section, stay high, and as long as you can keep your radar cross-section very low, no one's going to notice you're there. You'll have to work the daytime visibility as well, but then you'll be all right. And 400 watt hours of batteries weighs quite a bit. So I kind of looked at what battery technology is out there, and I'm familiar with some of the lithiums. I mean, there's a Japanese company that makes the batteries for satellites. They also happen to be, I think, the ones that make them for the 787. Uh, those aerospace lithium ions have excellent temperature performance, uh, very good cycle life, and they have a lot of published data online because they do extensive environmental testing and extensive cycle testing to ensure they have the reliability that a satellite isn't going to fail due to their battery systems, or an aircraft battery system is going to fail or catch on fire. And the only issue is that they're only about 100 watt hours per kilogram for those. Tataran, hey, we've used Tataran before on space applications. Tataran powered a lot of the data loggers on our MISSI experiments, and they have beautiful temperature range and excellent reliability, but they're only 50 watt hours per kilogram. Consumer off-the-shelf COTS, those batteries have terrible cycle life but excellent energy densities. A good middle ground, and the one that I would run with, is automotive grade batteries. Automotive grade batteries have good cycle life. Their temperature range isn't wonderful, so you'd absolutely have to have some heaters and some insulation on there. But at 130 watt hours per kilogram, that's all right. And so A123 Systems sells some batteries that seem prime. And then for the solar cell thin films, SIGs or cadmium telluride, either one of those would be okay. I just picked the cad telluride thin films because they're very inexpensive. And then the balloon material, you have to pick a hydrogen compatible material, which isn't that tough to do. But you want something that has a low permeability to hydrogen. And PVF and PVDF are both excellent choices. I stole somebody else's slides. I mean, PVDF is used outside all the time because it's extremely UV stable and it's very tough. So you add into that guy's slides that it's a widely available low permeability hydrogen and helium and excellent ozone resistance, and then on top of that, it happens to have good adhesion to aluminum, and it's a good thermoplastic for heat sealing and welding. It's a well-rounded, good choice of materials. The loss rates, if we look at the balloon that I'm pitching for carrying 8 kilograms of weight or 8.5 kilograms of weight, it's going to be like 211 cubic meters. So the loss rates end up being just over 1 liter of gas a day at altitude. So that's a cubic meter in 2 years. And hydrogen, it's useful. It's cheap. It's a lot cheaper than helium, or lot cheaper than helium. The helium, I think, I ran the number as being about $200 per 1,000 cubic feet, although it varies. I have no idea what the retail price is, but About 1,000 cubic feet is what I'd look for my balloon. So $200 for a balloon is way too much when I'm looking for a price that's in the range of 2,000 total for the whole thing. Hydrogen, however, is cheap and it's very much available. So you can get a hydrogen generator, basically a reformer that runs on propane and steam, or a reformer that runs on methanol and steam, and get it on the back of a small truck so that you can have field production of hydrogen wherever you need it. The other nice thing about methanol reformers is that they can be made very, very small. They're small catalytic methanol reformers that people are building for laptops and for fuel cells, right? You generate hydrogen gas, you use the hydrogen gas on a fuel cell to generate electricity. And this is a picture that I pulled from Pacific Northwest National Labs. I think it's intended for like cell phone applications. It's an extremely small catalytic methanol reformer. One nice thing about methanol reformers is once you get them going, once you put the energy in to get the reaction started, that's it. You don't need to put additional electricity in. It's a net energy positive reaction, so it warms itself as it runs. So controlling the optical properties, that's been done before. In fact, the French CNES, they made the mirror balloon, the Montgolfier Air Infrarogue, so I guess the infrared Montgolfier. And that is kind of like their infrared, extremely thin film hot air balloon, where they put it at altitude and then they used the infrared earth shine to warm the thing and keep it afloat. And so I think they had some extremely long duration flights on these things in the 70s and 80s. And so the concept of controlling your optical properties of your balloon, I mean, that's been done before, and I think it could be done better. You could fill this thing up, minimize the absorptivity of all sources, and hope that you can get conduction, convection to the air around you to dominate. So to do that, you'd want to minimize the absorptivity and emissivity, and you can do that pretty well, I think, with aluminum, with not much surface coating technology behind it. Just aluminized Kapton has been shown to have well-matched absorptivity and emissivities that are less than 0.1. So the electronics you have are essentially, you'll have a power management system, which isn't going to take much energy at all for your battery, motors, pumps, and you'll have a power supply system, which should probably be a single set of power supplies that cover everything for 1.8 volt, 3.3 volt, and 5 volt. So centralize your power supplies into one unit rather than using individual buck and boost power supplies on different boards. And you'll want to shoot for the most efficient power supplies you can possibly get. Even if you have to sacrifice weight, no big deal, because you'll gain it back in terms of battery weight later. So the power consumed by the processor, I imagine that's going to be very low, because it seems to me, in just routing data around, everything you need to do could be done by an FPGA or an ASIC or probably a pretty low power processor by today's standards. And you may even be able to roll extra functions into that FPGA, like power management. And all that should be doable for under 2 watts. The RF, both the access link side and the backhaul side, that is going to be dominated by the power amplifiers. Hopefully the baseband and the RF side are relatively low power, but the power amplifiers, those will probably be the power drivers for the system, and you'll want to fight for those to be as efficient as possible. So I borrowed some more slides from Boeing here, non-proprietary. And so what you see is flash memory. That is also something that's upset. And what happens is you can change the voltage of the memory stored in NAND flash. So and what the graph tells you is that modern technology is more susceptible than old technology. Multi-layer flash is far more susceptible to radiation than single-layer flash is. And so avoid multi-layer flash. And latch up. Latch up is where you'll freeze up a CMOS device because you'll have a parasitic structure that'll form between two transistors. Now, I imagine most of the things that you would use on this system would be very low voltage cores, 1.8 volt or 3.3 volt CMOS. And in that case, your primary concern is not that you're going to burn this part out, it's just that you're going to freeze up those transistors and cause some serious errors in the functioning of that device. Cosmic rays and heavy ions are major drivers of this, and so I stole another slide here. What you see in terms of mean time between device latch up in flight hours, that is scaled to 40,000 feet. It will likely be worse at 65,000 feet. And it's significant enough that it should be addressed. And the way to address it is simply put in watchdogs that every 100 milliseconds or every 500 milliseconds that just interrogate your CMOS device and make sure it's functioning normally. And if it is, it does nothing. But if it shows abnormal operation or if it shows that it's not responding, then it just resets it. And so in that event, you'll reset your node, it'll turn the power off to the devices, turn it back on, and then everything will reset and it'll work again fine. So a little bit about me. I work at Boeing in Seattle. I've got 13 years experience in the same group here that I hired into when I came out of college. So, and that's the Electromagnetic Effects Research Group. And so I've done mostly research tasks, but a little bit of program work on the side as well. EMI, EMC, which is electromagnetic compatibility. Lightning strikes to aircraft, high power microwaves for military programs, and then I've done a handful of spacecraft work too, space work, some satellite programs, and then also some experiments on the space station, Missy 6, 7, and 8, as well as a lot of sensors design work. I'm a physicist, but I do a lot of electrical engineering. So lately I've been working a lot on ultra low power electrical sensors and current mapping stuff.